A few announcements first. Um, Reminder that next week we will not have a Zoom meeting. Um, so there'll be an assignment um, pushed out probably Sunday night for next week. And then, I know you're all disappointed, but then we have to go on winter break for about a week and a half. So this will be your last opportunity to see Mr. Gingrich's lovely face um, before the new year. So also, I think as you looked or saw in Schoology, I just have the one link for classes. So if you decide you really would like to sit in on the A group class, you can certainly do that. But then still remember to do that attendance question through the counseling office, um, because I won't be taking attendance for you on those days. All right. So this section we're going to talk about today, linear approximations and differentials. We've done some work with linear approximations. We just didn't call them linear approximations. Basically, a linear approximation is using the tangent line to approximate values on a function. Differentials, we'll see here in a little bit what those look like. So a linear approximation, we can use a tangent line at the point a f of a to approximate values for some function f of x when x is near a. The equation of the tangent line, and this is just one form, y equals f of a plus f prime of a at x minus a. And this form is actually the point slope form of a line. If we think about the point a f of a, the slope of our tangent line is f prime. So we could rewrite this equation in point slope form. Y minus the y value, which is just f of a, is equal to the slope times x minus the x value, which we're told the x value, we're using a. So that's where this formula comes from. It's just adding then f of a to both sides to get back to the original form here. So we can use that approximation. Our function f of x is going to be approximately equal to that linear equation. That is called the linear approximation or tangent line approximation of our function f at a. And that equation for that line can be rewritten as L of x, and that's just called the linearization of a function f at the value a. So here's how we might use that idea. Find the linearization of f of x equals the square root of x plus 3 at a value a equals 1. And then use that linearization to approximate the square root of 3.98 and the square root of 4.05. Excuse me. So we can find a few of these values. We can find f of a, which is f of 1. And let's see, 1 plus 3. I think that's 4. And then we take the square root. This is our f of a. F prime, I'm going to take f prime of x first, and then I'll evaluate it at a. So we have a power rule. So we bring the power down, take x plus 3 to 1 less power, and then technically it's a chain rule. So we would need to take the derivative of the inside. And what is the derivative of x plus 3?
Just be 1.
Just be 1, right, right. So that's why we generally don't write it, but just to be very clear, we get 1 there. And now I am going to evaluate that at the value 1. So 1 plus 3 again is 4. To the negative 1/2 would be 1 over the square root of 4. So I have 1/2 times 1/2, which is 1/4. And for these, sometimes it's better to use the decimal approximation. You don't have to. Just sometimes it works a little bit easier. So our linearization is f of a, which is 2, plus f prime of a, times x minus a. All right, now to find the approximation for our, excuse me, for our 2 square roots. Excuse me. To figure out our x value, sometimes it'll be pretty clear because our function will just be x something. In this case, it's x plus 3 to the 1/2. So in order to make the inside here equal to 3.98, what would I have to plug in for x? Basically, what I'm asking you. What? Go ahead.
0.98.
0.98. Yep, exactly. And you could just very easily plug that into a calculator. and get 1.995. Now, how good is that approximation? If I find the square root of 3.98, my calculator says that is 1.994993734. So our approximation is within one 1/100,000th of the actual value. So a pretty good approximation. For the second one, again, what value would x have to be so that the inside of my square root is 4.05? So 3 plus 1.05 would give us our 4.05. And again, I could plug that into a calculator. And I get 2.0125. Now, before I check that approximation, it should make sense in both cases. The 3.98 is less than 4, and we know the square root of 4 is 2, so we're a little bit less than 2. Here we're a little bit more than 4. The square root of 4 is 2, so we should be a little bit more than 2, which we are. And again, that approximation, 2.0124618 on the calculator. So within 4 100,000ths of the actual. And the further we move away, the larger, or I shouldn't say larger, the further our value we're plugging in for x is from 0, the less accurate our approximation is going to become. So if I wanted to approximate the square root of 8, I wouldn't use this linear approximation. It wouldn't give me a very good approximate answer. All right. For what value of x is the linear approximation accurate to within a half? So this is a little bit more interesting. I'm going to, well, so we want to know our linear approximation is within 0.5 of the actual. So we could be that's not how I want to do it. So our approximation could be greater than the actual minus 0.5 or less than or equal to the actual plus 0.5. So just taking that margin of error, adding it and subtracting it from the original and comparing it to our linear approximation. We could solve that algebraically, but we're not going to, or I wouldn't advise doing it that way. It can get quite messy quite quickly. Instead, what I would do is use my calculator and I would graph the three different equations. So I would graph the square root of x plus 3 minus 0.5, 2 plus 0.25 times x minus 1, and the square root of x plus 3 plus 0.5. And if I just graph that on the normal window, I think you can see that the red line, which is my linear approximation, doesn't ever cross the blue graph, but it crosses the one in black in two different places. So what I want to do is find the x values for those 2 points of intersection. So again, one of our all-time favorite functions on the calculator. If I go second trace, I can use option 5 to find points of intersection. I don't want the blue graph. I do want those two. And my first guess is this point right here. 3 decimal places on the AP exam, so negative 2.657 as an approximation. And now we'll find that other point of intersection the same way. So second trace, intersect. And get over there for our guess. 8.657 as our upper limit. So we actually have a pretty good range. Basically what this is telling us is we could approximate the square root of 0.343 up to 11.657 and still be within 1/2 of the actual value of that square root. Yeah, pretty interesting to me anyway. All right, differentials. So for differentials, basically we're still taking a derivative. The differential is just dy, and it is defined in terms of dx by the equation dy equals the derivative of our function f prime times dx. And we can determine the value of dy if we're given the value of dx and a specific value for x. Basically just plugging in and solving for whatever piece we need. All right. The error in a given measurement is denoted by dx. So one of the applications for differentials is approximating maximum error in a measurement, like in volume, given an error in a single linear measurement. And we'll take a look at one of those examples here in a minute. All right. Sometimes relative error makes more sense. Ooh, I think I skipped a page. Let me just double check. Nope, guess not. Okay, relative error, you would take the error that you calculated and divide by the total value. The example we're going to do uses volume. Excuse me. All right, so here's our example. The radius of a sphere was measured and found to be 21 centimeters with a possible error of 0.05 centimeters. What is the maximum error using the value 21 for the radius to compute the volume? So remember, the volume of a sphere is 4/3 pi r cubed. And we're going to use differentials to calculate or estimate that maximum error. So don't calculate the error at 21, or the volume at 21, and then the volume at 20.95, and then the volume at 21.05, and try to find the maximum error that way. Instead, if I take the derivative, actually the differential, so instead of v, I get dv. On the other side, 4/3 pi r cubed. I have my 4/3 and pi are just constants. Take the derivative of r cubed. Be 3r squared dr. And yes, the 3's cancel, which is kind of nice. Whoa. So our maximum error is going to be 4 pi r, which is 21, times dr, which is our error, 0.05. In this case, I'm going to leave the pi in my calculation, just because it's more accurate. So if I calculate that, 4 times pi, which I'm not going to do, times 21 squared times 0.05, 88.2 pi. Again, if you want the estimated value, 277.088. So that's an approximation. So if we found the relative error, that would be our derivative for pi r squared dr divided by the actual volume, 4/3 pi r cubed. Pi cancels. 2 of the factors of r cancel. And the 4's actually cancel. So what I have is dr in the numerator. I have 1/3 in the denominator. So I'm going to bring the 3 to the numerator over r. And I know what those values are from the problem. dr is 0.05. R is 21. So we can approximate the relative error, or we can find the calculate the relative error. Three times 0.05 divided by 21. And that's 0.007. On the AP exam, that's where we would end the rounding. So that's the relative error. And then we could express that as a percentage rather than as just a decimal. And so our error is about 0.7% of the total volume that we calculated, the maximum error. So all in all, not a bad measurement. You know, relative error less than 1%, that's not bad. All right, homework. Questions? You're such a talkative bunch.